very much forward to listen to your session.
Thank you, Ben. So welcome everyone, welcome to this session on categorical data encoding for regression models. Let's jump right in. So I'm a SharePoint and Power Platform engineer, usually, but I'm very much passionate about analytics and everything related to BI and machine learning. So that's why we are delivering this presentation today. Feel free to check out my profiles. They're listed here, and as Ben mentioned already, I have pasted a link in the chat for this presentation. So you can download it, and then you can also check out the code later if you want to play on your own. So what are we going to look at today? This is the agenda that we have for our topic. I'm going to do an introduction in terms of justification and terminology. Then, of course, it's the core for the encoding methods and the demo. And finally, we're going to discuss the results, and we're going to mention a couple of words about our future work. So why are we actually tackling this topic? To understand this topic, we need to first look at what we call tabular data, and you should really not confuse. It's the same word, it's the same term, but don't confuse it with tabular services or any other proprietary Microsoft product. Because here we're talking about the hardcore term. So what is tabular data? Tabular data, here on this slide, you can see an extract from maybe a big table that is a 3x4. So you have 3 rows and you have 4 columns, or we also call these 4 columns features. Some of these features are categorical, such as feature 2, 3, and 4. And feature 1 is actually a numerical feature, so it contains only numbers. This is what we're going to work with today. Also, a 3x4, so this is what we call the dimensionality of our data set. So in this table in particular has a dimensionality of 3x4. Now, what is the challenge that we're facing when we're working with tabular data and we want to feed this tabular data into the regression model? Typically, ideally you will have numerical data, but in reality, you would also have text data, and you must represent this text data in some numerical way in order for this regression model to be able to process this data. What I have found out by trial and error, of course, and what you can find in the literature as well, is that simple forms of representation of the text data tend to produce very poor predictions, and we're going to actually see this in our first categorical data encoding method. So we have to find a numerically consistent way to represent our various features and feature values, because this is also related to dimensionality, as I already mentioned the concept. So this is the core of the challenge, but also what about cardinality? I'm going to talk a little bit more about cardinality in the next couple of slides, but what about cardinality in the sense that it's quite important, because this is the number of unique values that you have in a set. And here, when we talk cardinality in a set, we actually mean a particular feature. So if we have a very big number in terms of cardinality, we are going to get another challenge, which I'm going to show you later. And also, how are you going to tune your neural network regarding in line with the actual encoding method? You have 2 considerations here. The first one is that ideally you want to get feature agnostic results. However, this is really hard to achieve. And also, you must keep in mind, if you're regardless, actually, if you're new or not to this, that this tuning process, hyperparameter tuning, is a very much continuous process. So it's not something that you do and forget about it. But if you want to really polish off your models and continue deliver excellent results, that's a continuous process. And the challenge here, also, that's a point in terms of the challenge, is that when you get a certain categorical data encoding method, it introduces something else that you need to take care and configure and incorporate into this continuous process. Now, in the next couple of slides, I'm going to give you a very brief, it's not even a crash course, it's just a super brief introduction into some of the terms that I think we need to know in the context of this presentation. Each one of these terms is worth at least a separate presentation, but we're going to cover them for the sake of the categorical data encoding methods. So this is the list here that we're going to discuss a little bit in the next couple of slides, and then we're going to move to the actual methods. So we have prediction, cardinality, and you can see the rest here. So it's 7 of them. Okay, so the first that I want to mention is prediction. So what is actually a prediction? In principle, we're talking about prediction in the context of neural networks, because a neural network by itself, it can compute, and it actually represents a function. So ideally, a neural network, in theory, can do everything that a normal digital computer can. The practical applications, for example, involve supervised learning as compared to unsupervised learning. So here we are actually discussing a case of supervised learning where part of our data is what we call the label, and this is what we want to predict. On the other hand, in other models, they may be related to unsupervised learning, where you are trying to make sense of the data without having anything to actually predict or classify. So because this is a supervised type of learning, we can work with the so-called regression. So actually, regression is a type of supervised learning, and in this type of supervised learning, we're trying to predict a single scalar value. So the model will output just one value that is actually our prediction. That's, for example, as compared to classification models, which can be, for example, binary or multi-class classification. So after a successful training episode, you can present input data to your neural network, and then the neural network will give you an output with a certain degree of certainty, with a certain degree of confidence that this is actually the good result after the prediction. Cardinality, as briefly mentioned in the very beginning, this is the cardinality of a set is the measure of the number of elements in the set. Here we're talking about cardinality in the context of our features. So when we talk about the cardinality of a feature, we're actually talking about how many unique values we get in that column or in that feature. And that, as you're going to see later when I open the code, is going to be quite critical for it has a lot of impact on each model on one hand, and also is quite critical for the performance of the actual model. Next, we have the types of layers. So every neural network has 3 types of layers. That's the input, hidden, and output layer. And typically we work, at least in this demo here, I work with 2 hidden layers. That's, again, quite a subject of discussion, but in literature, you can see that frequently, again, it depends, but frequently you can see that 2 hidden layers can give you a relatively good approximation. And also, on the other hand, the more layers you introduce, that doesn't guarantee actually that you're going to get a better result. So these are the types of layers that we're going to work with. We have 2 hidden layers here in our case. And just to give you a quick demo in terms of the layers, I'm going to show you here. This is a TensorFlow playground, and I like it because it really gives you a great idea visually what is the input layer, which is right here in this case. This is the input layer. We have 2 hidden layers, as mentioned already, and then we have an output layer, which is actually here. And this, in fact, is, if I configure it like that, is actually something very similar to what we are doing. Of course, you can also play with this activation function, regularization, and so on. These are parameters that I'm not going to talk very much about in this presentation. But you can see live here, if you play around a little bit, what happens and how the output changes if you give it more hidden layers or if you change the number of neurons per hidden layer. And yeah, as mentioned, number of neurons, that's also something quite important, and also that something that you're going to see all over the Python code later in the presentation. So in the input layer, that's always the feature count. So that's the number of features, the number of columns, if you want. Then you have the hidden layers. So the number of neurons in the hidden layers is a hyperparameter. I use 40 for the one-hot encoder and 20 for the rest, and it's different for the entity embeddings. But this is also worth a separate presentation, how many neurons you should use in the hidden layers. So just accept it as a given. Here we use 40 and 20. An output, because it's regression, we have only one in the output layer. What about hyperparameters? Much of what we actually mentioned so far is pretty much a hyperparameter, but they have different types. So for example, they have varying upper and lower bounds. They can be positive or negative. They can be an integer or a floating point number. For example, the epoch count, that's the overall time that you use to train your network, also is actually a hyperparameter. Or in fact, they can be also categorical, such as the type of function that you're going to use. So what's important to mention here is that our categorical encoding methods on their own, they actually introduce a separate set of hyperparameters. For example, we have the smooth mean weight that we're going to see in the target encoder. We have the hashing function. We're going to see it in the hashing encoder, and we have the embedding size hyperparameter in the entity embedding encoder. So hyperparameters, again, that's a huge topic. There's a ton of information online, how to pick default values and how to tune them. And again, as mentioned, it's a continuous process. Moving on, it's also worth mentioning the activation function. You're going to see that in the Python code in the notebook. I'm using the ReLU function, which flattens pretty much the output. So if you introduce a negative value to that function, is going to return a 0. And we also use the linear activation function. So yeah, whatever is the input, the output is actually equal to the input. We only use the linear function, and we very much typically use it in regression models from the last hidden layer to the output layer, because you don't really need to transform that output anymore or activate that output anymore. So these are the two functions that we use here. And yeah, it's also worth noting that if you don't use an activation function or just use the linear function, if you experiment on your own between the different layers, except for the output layer, then you're not doing much. It's not a neural network. It's just a transformation. My point is, the activation function is quite critical. It's a very important choice in your setup, in your neural network architecture setup, in order to deliver good results ultimately. And next, we have to mention the loss. That's one of the most, everything is important, but in this context here, it's very much important because this is what we use to actually measure the performance of our different models and to actually evaluate which categorical encoder can we recommend, or which categorical encoder actually gives us better results. So this loss, that's also what we call the root mean square error. And regression models rely heavily on that metric. There's also other metrics for loss, but here we work with that particular metric. Also for other neural networks, for other models, you have different types of loss, but there is always some sort of numerical expression of what you're trying to achieve. And what you're trying to achieve is the prediction. And to gauge or to evaluate that prediction, you're working with the amount of loss. So here you can actually see that visually. In our regression model, you can see that visually here. And here I can show you that if, for example, this is the regression line that we draw among our data points, and we want to make a prediction here. So if this is our prediction, these are the different points that we're trying to predict. Naturally, they are not there. They should be close to the line, but they're somewhere along the line or top or below the line. So the difference, right? The difference that we have like that, this particular difference, and this difference, you get the idea. For every single point that is not on the line, this difference is what we call the loss. So the difference between the actual and the predicted values. So let's get into the actual encoding here. So again, yeah, this is a curated selection. So there's like a ton of methods that if you, just a quick search on Google is going to give you a lot of results. This is a certain selection that I did and tested out, in fact. So it's a good starting point. If you have such a task, that's a good starting point. The first one that we're going to look at is the so-called one-hot encoder, where for each unique value in each feature, we get a new feature that will contain either a 0 or a 1 for that corresponding case. For the corresponding case means for that particular row in the data set. How does that look like in practice? You can see the one-hot encoder here. So if this is actually the source table, the source data set, what we are doing is we're trying to transform our categorical values, which are caller ID, caller ID2, caller ID3, and we're trying to encode them. And what the one-hot encoder does is it converts or transforms each of those values into ones and zeros, but also it increases the dimensionality. What does that mean? You see this, the dimensionality is going to grow. So if here, this is an extract, but again, if here it's a 3x1 dimensionality, here it becomes a 3x3, and this is such a simple example, and it's already grown 3 times. But you can see that for caller ID 1, for case 1, we have a 1 because that's exactly what corresponds to that case or that row. And for the rest, you get a 0. So accordingly, for caller ID 2, you have a 1, and for caller ID 3, in row number 3, you have a 1. So this is the simplest method. And now let's take a look how this works in practice. So this is the notebook that I'm going to use for this presentation. The link for this notebook is in the presentation itself, one of the last slides. I'm going to also point it out at the end. I'm not going to go into much detail about the other stuff that's happening here in this notebook. You will get the chance to play with this on your own. It's shared, and this link, I'm not going to delete it, so you can export it as a Jupyter notebook and import it somewhere else if you want to, such as in the Microsoft Machine Learning workspace. So first of all, we are doing some data preparation, and first of all, we are actually doing the plotting method here. So we have a couple of utilities that you can on your own. I installed the category encoders library. This is what I'm using for some of the methods. And then we have the data preparation. So we are doing just a couple of basic things. We are dropping some of the features. We are dropping features that have no values. That's, again, a decision that the data scientist takes. You can fill the blank values. You can drop them here. I've decided to drop them. And then we get a preview of what this data set looks like. And this data set is actually coming from a support ticketing system. So what you can see here is that every row is actually a support case. So we get the relevant information about every support case, such as has it been reassigned, how much, how many times, has it been reopened, how many times, did it make the SLA, true or false, what is the caller ID, in this case that's anonymized. We have the open date time, system updated by, and a ton of other metadata that I believe it's quite important if you want to predict, because the end goal here is to try and predict what is, how much time is going, the next support case is going to take. That's what we're trying to do here. So we want to leverage all this information and all of these features that we get here, but I can see already that everything is, pretty much everything is categorical. So pretty much everything is text. And pretty much everything is relevant because we are interested in location, where the user is creating this. We are interested in the category, subcategory, symptom, impact, urgency, and so on. You can also explore this more separately. So this is pretty much what the data set looks like. We are calculating the case duration by subtracting open.dat from closed.dat. Here, we are standardizing the case duration. This is again worth a separate presentation, so I'm not going to stop here, but then from trial and error, I found that it gave me better results if I actually standardize the case duration. We encode the date in terms of week date. Yeah, that's a decision that I took. You can experiment with another type of encoding for the date. Made SLA is obvious. That's going to be either a 1 or a 0. And then here we already are beginning with the one-hot encoder. So this is our first method. We first get a list of the categorical columns. This is our list here. Okay, maybe I should zoom just a little bit like this. Probably it's going to be better for you. And then we're applying the dummy encode method. So this is actually the dummy encode method is not part of, if I scroll all the way up, is not part of this category encoders library. The dummy encoder method is actually part of pandas. So it's quite, yeah, they use it a lot. So it's actually part of pandas. You don't need to install any other libraries. And this is the result that we are going to get. So we iterate over each feature that we want to encode, and this is the result. So this is the resulting data set here. And you can see that every column or every feature has already been transformed, so it doesn't have text values, but it contains only ones or zeros. But the other thing that you're already noting probably is the hugely increased dimensionality of the data set. So we started with 20 columns, and now we have 8,011 columns. And this is a problem, because when we go ahead and generate X and Y, so here we are on one hand separating our predictors from the label. So from what we are trying to predict, this is the Y value. We are also creating the train, validation, and test data sets. But when we actually try and train the model, you will not see any results here. And the reason for that is because this particular environment actually has only, Google Colab gives you about 12 gigabytes of RAM, and 12 gigabytes of RAM is absolutely not enough to process this data set and to give you some sort of prediction. So in fact, this is absolutely catastrophic for what you're trying to do, because this is not going to give you any results. I managed to run it with about 25 gigabytes of RAM, but that, again, the fact that I managed to run it doesn't guarantee good results. So this is not efficient. Bottom line, this is not efficient. In this case, it's not giving results. If we were to increase the amount of memory, it will give us results, but from my previous tests, the results were not good enough. I'm going to show this in the comparison section. So therefore, the plot metrics method here is actually not giving anything, because there is no model instantiated. So this thing is not working for us. So for now, I can say that this is good if the cardinality of the features that you want to encode is not that high. So now let's look at the next encoder. The next encoder is the target encoder. The target encoder calculates for each feature value an average of the corresponding values in the target variable, which is the case duration. Then we have to replace each unique feature value with its according mean. It's quite a mouthful. It does take some time to figure it out. This is what it looks like in practice. So this is the target encoding process. We have to take the mean for the target value. We have to calculate that. So first, it's calculated over the whole data set. Then the count and the mean of the target value are calculated, but this time we are actually performing a grouping, because we are doing that for each unique value. So we are again leveraging, not leveraging, but we are again counting on the cardinality, and it's really a factor. It's really a big influence in this model again, but not as much as in the previous method. And finally, we have to calculate what is called a smooth mean according to this formula, which you can examine on the next slide. So this formula is actually taking a lot of metadata values, let's call them like that, from our data set. So these are all numbers that we already have, such as the number of values, such as the estimated mean that we just calculated, the overall mean that we again just calculated. And however, here we have one hyperparameter, and that's, you see that M, so that's the weight. So that's why we call it the weighted or the smoothed mean, because that's a certain amount of, that's a certain number that modulates this mean. And with this number, you can fine tune the representation, the numerical representation that you're going to get out of the categorical values based on this method. And unfortunately, it's not, I would say it's not very straightforward, because there are no bounds to this number. You can give it a negative number, you can give it a positive number, you can give a 1, you can put 1,000. It's about experimenting, depending, of course, on your data set and on the features in the data set. So let's take a look at the target encoder. So I'm just going to jump to the target encoder. So this is a target encoder. And yeah, just another clarification actually. So everything here you see is actually pre-run. That's for the sake of saving time, but I guarantee that everything here works. So when you download this, and you can run it and just get a feel for it on your own. So the first block here is the actual method. So this is the method definition in Python. Python is what we usually, as a language, what we usually use for such scenarios. I'm sure it can be done in other languages such as C#. But Python is much more practical in such scenarios. And of course, you can also run it on the Microsoft Data platform, such as in the machine learning workspace. So this is the method. As I mentioned, this method needs to take the count and the mean per every group. And you can clearly see that on this row here, because this is actually the piece of code that calculates the mean of the target according to every group, which is according to the cardinality of that feature. In the next code block, we are assigning that weight. So here I'm working with a weight of 5, which is pretty much arbitrarily assigned. It can be easily be 4.5. It can be easily be 4.65. So this is something that you need to kind of feel and adjust first randomly, and just get some results and then try it again, see if it's better or if it's getting worse, and then adjust accordingly. But a lower tends to be more overfitting. So finally, the model is going to overfit more if you give it a lower number. And higher, of course, it doesn't guarantee that it's going to be the best model. But this lower and higher, this doesn't mean anything. So again, there are no bounds here. We make a list of the encodable columns, and for each of those encodable columns, we calculate the smooth mean. So for each feature value, we calculate the smooth mean, and this is what we end up with. So this is a preview of the already encoded results. So as you can see here, apart from these features that were already clear, that were already numeric, we end up with a lot of numbers that for the human eye don't really make sense at all. But hopefully for the model, they will make sense, and they will make much more sense than the other methods. Most importantly, we don't have an increase in the dimensionality, because we are actually substituting, right? So we don't have extra columns, and this is going to be good for the final prediction. Again, we have to generate an X and a Y. The Y is the case duration, that's the target. I'm also doing the 20% split. That's kind of also standard, good practice to do that. So we do that, we train our model, right? We get a training episode for 20 epochs. So I'm just doing 20 epochs here. The reason for that is so we can actually zoom into the beginning of the process, but ideally in practice, 20 is not going to be enough. maybe you're going to need 100, maybe you're going to need 500. That's again a hyperparameter that the practitioner is supposed to choose, right? We evaluate the model, and most importantly, we plot the metrics, right? So this is what we are after ultimately, so we can actually evaluate our model. We are also after, of course, this overall number here that we get, the test loss, right? So this is what we are really after. It's the number that represents the test loss. But this plot here really gives us a lot of information about what is going on in the model. And so far, the results look optimistic, right? Because we have a training loss that is steadily decreasing, but also is not approaching zero. So it's kind of converging maybe somewhere in the future. We have a healthy, I would say, validation loss. That maybe one problem is that this difference, which is called the generalization gap. So this generalization gap, ideally, maybe it should be lower, but yeah, there is no rule about it. Because ideally you want to look at this as something that again converges but doesn't touch the training loss. So this looks promising so far. We also get a model summary. So these are standard methods that we have in Keras to get a model summary for the number of parameters, and we finally get a full representation of the model. So as mentioned in the beginning, we have an input layer. We have two hidden layers with 20 neurons, the first one with 20, the second one with 10, and we finally get an output layer with one neuron in it. So this was the target encoder. So far, so good for the target encoder. Now let's move on to the binary encoder. So what the binary encoder does is it converts each categorical feature vector into its binary representation after substituting each value with its ordinal representation. So again, a mouthful here, but this is how it looks in practice. So binary encoding process, we have to assign ordinal numbers to the values. So we have category 1, 2, 3. We have 1, 2, 3. Accordingly, we have to convert those numbers to their binary representations, and we have to extract the new feature vectors. Now, on the next slide, I hope that it becomes a little bit clearer. So this image is available online. You can check the source. So here, if we have hot, cold, very hot, and warm, these are, first of all, cardinality of this feature is 4. Second of all, that means that we have 4 unique values. But what we are after is this binary representation of the actual number. So this is what it looks like. And because it looks like this, we only get 3 new features, which are right here, 1, 2, and 3. So this is how we're actually able to encode, and you can track and you can see that for hot, which is 001, we get it right here, and this essentially represents hot into the model in terms of a number. So now let's see how the binary encoder performs. If I skip back to this notebook, binary encoder, again, we have to prepare our list of encodable columns. And this method is pretty much encapsulated, but the source code is available online. So the method just wants, as an argument, a list of the encodable columns, and you're going to end up with your transformed data set. This is what the transformed data set looks like. It doesn't make a lot of sense anymore because you have a lot of extra columns, and you can see that they have like ordinal numbers because these are actually the encoded feature values. And of course, we notice that the dimensionality here has also grown, but it has grown much more moderately. So we have only 122 columns, which I hope is going to be good for the model. So we go ahead and generate X and Y. Again, here we train the model. We have the same thing here. Yeah, one thing you notice that it does start with a little bit higher loss, but that doesn't necessarily mean anything, at least for now. We evaluate the model and then we plot the metrics. So this is the metric metric plot for the binary model. You notice already that the curves look differently in the sense that this one It seems that it's steeper, but you can also say 100% that this model definitely needs more time. So this model definitely needs to continue to be trained up to, yeah, maybe epoch 100. And also, what is quite important to mention is that this here seems quite big, so this may be a reason for concern, but that's also another reason for us to continue training this model for at least, I would say, at least 100 epochs, just in order to see if this validation loss is actually going to, what direction is it going to take, right? Is it going to go down or is it going to go up? And because what we want to have is converging validation and training loss, but not touching. So they should stay apart. So this is, yeah, we can say that this is also not bad for now. We have the model summary, and if I draw the visual representation of the model, it's going to be absolutely the same because you have the same amount of hidden layers and you have the same amount of neurons in each layer. So that was the binary encoder. Now let's move on to the hashing encoder, which is a little bit more complex. It uses a hashing function to map feature values to indices in the resulting feature vector. So after hashing, we can get the location in the vector we have defined by the vector size hyperparameter function. This is what it looks like. So we take an input feature value. So if we take the category feature and we take category 55, we have to hash the value. And you notice already that, yeah, okay, so what hashing function are we supposed to choose? Yeah, such a function that doesn't allow for collisions, just to be safe. So that's why I have chosen the SHA 256. It's an industry standard. You can experiment with other functions as well. And that's a hyperparameter in this model. So we get the hashed value, we extract the new feature vectors. So we have to convert from the hexadecimal representation to the integer representation, applying this function here. And then we have to assign ordinal numbers to the values in the vector by actually taking the modulo of this integer number times 15. Why 15? That's another. That's the other hyperparameter. That's the size of this vector that we are talking about. So this is what this is kind of a snapshot, if you will, from our tabular data. So we have the string value here, category 9. We have the hashed result, which doesn't make a lot of sense to our human eye. We have the integer representation, but what we are after here is the resulting index, which for category 9 is 4, for category 20 is 14, for category 40 is 5. So bottom line is that, again, we end up with a certain numerical representation out of this categorical value, out of this text value that, okay, for us makes sense, but for the model it doesn't. So 4, 14, and 5 to the neural network, yeah, that's going to make sense, and it can be processed by the model. So hashing encoder, we do the same thing here. We get a list of the encodable columns. We pass those columns to the hashing encoder method. And of course, we also have as arguments these hyperparameters that I mentioned, namely the hashing function, the vector size, and we get the results. So here, as very much in a similar way to the target encoder, we don't get an increase in dimensionality because we are actually doing an in-place substitution of the values. So dimensionality is not affected. So this is also good for us, good for the model, and good for the predictive power of the model. Again, we have to generate an X and a Y. We have to train our model here. So training is successful. Again, I do it for 20 epochs. And we have to evaluate our model. We can see here that this loss that we are getting is already higher than the other methods, but we are also going to discuss what higher means here. But ideally, this is not a very good number, actually. And finally, we again plot the metrics. And when we plot the metrics with the hashing encoder, we see two important things. So important thing number one is that for this amount of time, so for this 20 epochs that we have, so 20 is here. So for this 20 epochs that we have, we should definitely continue more. So that's one thing. But the first important thing, training loss has not improved at all. I mean, yeah, it has improved, but it's hardly, it's just below 1. So we definitely need more time because this thing needs to decrease so that the model can learn. But the second important thing, and it's a little bit unusual, but it's also kind of a cause for concern, is that the validation loss of this encoder has caused the model to predict better what it doesn't know. This is what this plot means, because the validation loss is actually lower than the training loss. So we have to see what happens in time. We have to see what happens in time. We have to see what, for example, yeah, for the 100th epoch or for the 1000th epoch, what happens in time. But this is a cause for concern, so we need to explore more or maybe fine-tune our hyperparameters based on our data. So this was the hashing encoder, and here is our final method. Our final method is the entity embeddings. The entity embeddings it should be in this presentation, but it's completely different because it requires a different network topology. It requires a different architecture based on the feature cardinality. So one input and one embedding layer are actually needed for each encodable value. So the model will look completely differently, and it's going to be much more complex as well. So entity embeddings. We have to establish an embedding size for each categorical feature. So that's kind of specific challenge number 1. For this, we actually use a method. In literature, you can see that, yeah, they say 50 should be kind of a good practice maximum size of this embedding vector. I would say it can be also 100, it can be 200, but ideally you wanna keep that value in check because you don't want to have a huge embedding vector. But the point is that for features of high cardinality, this embedding is going to be capped. So if the cardinality is above is 51, so if the feature has 51 unique values, this function is going to cap it at 50. And that's quite important because otherwise this model is going to be potentially, it can be huge. So the next thing that we have to do is we use the cardinality as input dimension, embedding size becomes the output dimension. And the network actually takes care of this for us. So this actual encoding and the values in the vector, I'm going to show you the vector in 2 slides, is actually what the network does for us. As a next step, each feature is converted into a list. So there is an extra transformation here, and also there is an extra type of neuron layer that we are using here, which I'm going to show you again. So continuing the process, finally we need a multi-dimensional array because we are working with all of the values. Its elements are lists containing the encoded categorical values, and this multi-dimensional array is actually what we pass to the model. So the matrices of the embedding layer have to be concatenated. I'm going to show you this in a picture because it probably doesn't make much sense like this right now. And the result is a huge dense layer with an input of size, the sum of all embedding sizes. But let's look quickly at what we call the embedding vector. So if we take the impact feature, for example, because it's a feature of low cardinality, so we have only 3 values, 3 unique values, high, medium, and low. And if we have an embedding vector like this, so we have we have 2 values in the vector, right, v1, v2. We have to, so not we, but we have to configure it so that the model can find the optimal values for v1 and v2 such that the categorical value will be correctly represented. So the advantage of this model is also what you need to be extremely careful about, because obviously this is very powerful. So you can represent whole bodies of text, because this is actually coming from the NLP domain. You can represent whole bodies of texts in terms of vectors, but you have to be very careful how you do that, because you have to take in mind your data set, your feature values that you want to work with, the set of the features that you want to work with, and everything that you want to achieve. So that's quite important. So this is a simple kind of an outtake here on this slide. But let's look at how it actually works in practice. So for the entity embeddings, we have some extra pieces of codes. We take the feature cardinality first, so that just for comparison, just to give you an idea. So for example, color ID, yeah, naturally that's a feature with a high cardinality, because you have a lot of colors, you have a lot of users. In this case, we have more than 50 to 100 users that have actually created a ticket. Then again, we have to make a data split. So we have to assign, we have to divide between what we have and what we want to predict. And then we have to define the embeddable columns. And this is this list transformation that I was talking about on the previous slide. But as mentioned, I'm not really going to dive deep into the code. And here we establish the embedding dimension. So this method calculates the embedding dimension for us, and the output just for a comparison. So we can look here, for example, let's take the impact, right? Impact unique categories is 3, embedding size is 2. So if I just go back quickly here to this example, impact feature has 3 unique values, but the embedding vector is going to be of size 2 according to this formula right here. So this is actually the core, or the starting point, if you want, of this method. So we have to generate a couple of new names based on the feature names, because we are going to use different types of layers. That's what we do in this code block. And finally, we define our model, which looks different. Unfortunately, we're not going to get enough time to discuss the specifics of this model. But what I found online when I was working on that, and when I was adapting that to my goals and what I wanted to do, is that this works okay, but it has a lot of differences as compared to the other models. So first of all, you have much more neurons here. You have an extra dropout layer, which is quite required in this case. And yeah, and also you have other things that are worth discussing, such as why is this input, with this hidden layer of size 512. But we're not going to go into details here. I'm going to jump to the network architecture. So this piece of code generates this model. Okay, so I'm going to zoom in because it's quite a big image. To just give you an idea of what we discussed so far. So we have the input layer, we have the actual embedding layer, okay, and then we have a reshape layer. And this is quite interesting because from the reshape layer, we go to a specific type of layer, which is called a concatenate layer. So the concatenate layer is essentially combining all of the already encoded embeddings into one layer and feeding that into the hidden layers of the model. And this is what is actually our representation, this concatenated layer based on each of those reshape. This reshape layer is actually converting the results from one dimension to another. But you can see here that it's much more complex as compared to the other encoding methods. But that doesn't guarantee that we're going to get good results. Okay, so let me go back to my presentation. Yeah, let's just discuss quickly the plot here. So after we train and evaluate, so when on the evaluation part, the loss is quite big. Okay, so we are not insured against such scenarios. The loss is quite big. This is, I would say, that's not acceptable. And also the plot here kind of confirms these not so good results. First of all, I would say this is quite obvious overfitting. Already at epoch 20, the training loss is decreasing very much and very rapidly, and it seems like it's pretty much zero here. So it stays like that, I would assume. Actually, it's not like that, it's more like that. So it's quite overfitting. And what is, again, more troublesome is that this validation loss is quite high and seems like it doesn't decrease, so it's not going to converge, because what we want to have is something like that. That's what we want to have.
Quick, you have about 10 minutes left.
Yeah, thanks, Ben. So we want to have a converging validation loss. That's not the case. So this is a cause for concern and essentially a red light that we either need to tune further this model, or I would say, but that's for this data set, that this encoding method is not particularly efficient for this data set. And that's also something that is quite possible and can happen in practice. Not every encoding method is going to be working right away for the data set that you introduce. So if we jump back to our presentation, here we have to discuss the comparison. So we have a table, a comparative table. In that table, I also included the starting dimensionality, because I also think that's something that needs to be, it's important to consider. So for the one-hot encoder, you can see here that we have a huge increase in dimensionality, and that the target encoder and the hashing encoder are much better in that regard. And this, okay, that's also good. But what's important for us is performance over these 20 epochs, right? In reality, it would be 100 or 1,000 epochs. So for 20 epochs for the target encoder, we get this number. So that's 0.5158. And is it good or is it bad? In the context of this model, my conclusion would be that it's good, it's okay, it's not excellent, but it's good, it's okay, it's a good basis. However, the others are not particularly good, especially the entity embeddings one, because this number being more than one essentially means that the model, the prediction of the model is going to be wrong every single time. So the target encoder, if we look at sort of a ranking here, less is better, of course, in terms of loss. So the target encoder is definitely the champion of this exercise, and I kind of left it like that on purpose because I want to make a point. So the one-hot encoder, you don't have data for it because it exhausted our RAM. So we didn't have enough memory at all to actually run this. So obviously it's not obviously, but maybe that's not a good choice for us. So the target encoder should be our practical choice if we want to take this further. What about the future? And if you want to get your hands dirty, so if you want to experiment yourself, what I would suggest as a first step, just check out the code, download this. You can create a workspace into Azure Machine Learning. You have to attach for the one-hot encoder a machine with at least 20 gigabytes of RAM, so a compute resource that has enough compute resource, so that you can run this. Import the data and the notebooks, and the data you can find at the University of California Irvine repository. It's openly available. And then you can experiment yourself as well with the other categorical encoders. Or alternatively, you can also go to the Azure ML Studio. I believe that's the old one. I also believe that they're kind of phasing it out. But it's worth mentioning because it has a built-in hashing encoder. And I would say that's for a reason, because the hashing encoder, if we just quickly go back, the hashing encoder, in this case, it ranks third. So in another scenario, maybe it ranks first and maybe it's quite good. So the hashing encoder is actually popular. And also in the Azure ML Studio, you can run custom Python code. And if you really want more and you're desperate to experiment with this and you're bored on your Sunday afternoon, you can check these links here. So coding systems for categorical variables. This, I would say, this is quite an exhaustive list of every possible model, every possible approach, every possible encoder that you have. So that's quite interesting. That's an article on in a blog all about categorical variable encoding. That's very practical. And here is the link to the notebook that we just discussed. So this is pretty much everything for today for categorical data encoding. And I would love to hear your questions if you have any.
Thank you very much. So far, no questions on the chat, but everyone feel free to drop them in.
Mm-hmm.
Okay, and there goes the first question. Going to be curious how you're going to take this one.
Mm-hmm.
So Wim is asking, how do I start as a beginner?
How do you start as a beginner? Okay, so if you wanna, let's make first a couple of assumptions. Assumption number one, if you want to predict something, so if you want to use a regression model, as a beginner, I would suggest start with Azure ML Studio. You can, for example, easily Google Azure ML Studio, and there's a bunch of tutorials for regression models and for making classification models. And this is going to give you a very nice primer. The data sets that they use are quite basic and they're all numerical, but you're going to get the point as such, right? However, if you want to up the level just a little bit as a beginner, then you can just open the Keras documentation. You can just try whatever actually the code that we have here, because this, I know it looks complicated, but when you really look at it and when you do it a couple of times and when you read the documentation, it's going to make a lot of sense. But also another advice for a beginner is also get the basics, the real basics. So that's the first 10 slides of this presentation. So that's kind of the terminology introduction. Get a primer for that. Online, again, there is a bunch of resources for what is a neural network, what does it do, and what are the elements, what is hyperparameter tuning. That's critical to understand as a beginner. And then you can explore as a regression. So for me, for a regression, this is an important scenario, because in practice, and if your boss says, I need you to predict this, and just hands you over a data set that is coming from somewhere, you most probably you have to do some, if not data engineering, then at least encoding. So that would be the second step. That's my answer. I hope it makes sense.
Wim, hope that answers your question. Otherwise, feel free to drop a follow-up to the chat. And of course, everybody else, if you have any questions, Chris is happy to take them. Unless you're all busy giving the session feedback, which I'm sure everyone will be providing as a little thank you for the speakers, especially here in the newcomer track. So Kuhn's got a question. So, so Kuhn's question is, do you agree that Visual Basic is vastly superior than Python?
I'm voting with two hands. Huh?
I think, in all fairness, we need to get usage stats on this. I think there's far more applications running VB than Python.
Yeah, legacy applications. If you say legacy
applications. I said applications.
Okay, yeah, okay. I think it's debatable, but yeah, we can discuss it over beer. So.
Good answer. You see, Ben, we've been training.
You had me at beer.
Training them well.
I have so many follow-up questions. All right.
And I have to agree, diplomatic answers was the last thing I expected from you to teach. But good. I see it's good that you've done so.
So thank you very much. As expected, this melted my session. Also, first direct feedback. I loved your slide layout. That was very nice. So again, everybody, please do provide feedback to Christo and all the other sessions that you've attended to date. This will conclude today's newcomer track, but there's one more session going on in all the other tracks, so feel free to check that out. Let me take the opportunity to say thank you to all these speakers and all the mentors, and also for Benny and his colleagues for having a newcomer track. I love newcomer tracks, as some of you may know. Thank you for having me as a moderator, and I hope to see you all again in person at next year's datamindsConnect.
Absolutely.
As much fun as this was.
Thank you for volunteering your time to come help us out. It's been grand.
Yeah, and thanks to Kun for helping me polish this whole presentation.